I'm supposed to be here, right? Yeah. Sure. So welcome to the Floating Marine Lab. This is a studio for architecture. We're very proud that we have a collaboration with the marine biology professor Rajan this year, from the Faculty of Marine Biological Science, and myself from architecture. So we think that this studio is important because we're talking about the ocean, and that's not very common in architecture. Maybe I should remove this, because this is not very good looking, right? To have all these buttons. Is there a way that I can, maybe I have to remove these buttons. Hide video panel. Hide floating meeting with you. Okay. Great. So the ocean is very important. The light comes from the ocean. It's absorbed into the heat of the sun, and it controls the climate basically, but we're destroying the ocean very, very fast. This particular area of the ocean where we live, more than half of the world population is in this area, and therefore we can have a big influence on the region. This project is part of a longer research project. I've been working on this topic since 2010 of building floating laboratory. Last year, the seminar studio, they built a floating laboratory made of bamboo and recycled material for 11,000 Hong Kong dollars, and it's all documented. And this year, we actually focus on the oysters, because oysters are a very quickly disappearing or quickly damaged ecosystem that's very, very critical. And so I'm very excited that the students are going to present you their work for this year, and we will continue to work on this project for a couple of years to come. So what I think this studio is very special is that we don't build architecture for humans, we build architecture for animals. It's not small scale, this is the actual scale. It's not a model, this is a real system, and it's actually going to be used, unlike a model that's not used. All the guests, I would like to invite you to scan these QR codes or follow these links that I will put in the chat. And I would like you to evaluate the work on the potential impact that it could have, innovation and creativity, how new and novel you think it is, the research, is this well documented, and how well it's presented to you, and then also the teamwork and how the students work together. And at the end, I'd like you to also give some feedback, and maybe you have some references that you'd like the students to see. All the comments will be shared with the students. So we have 30-minute presentation, we'll take a 10-minute break because we need to change the room. And then we have 10 minutes Q&A and, okay, 2 minutes, perfect. Without further ado, the students. Okay, 2 minutes. This one to go first. I'm going to start a stopwatch so people will have a
First, I introduce the geography of Hong Kong Oyster industry is centered around this bay.
Yes, I forgot to put the microphone myself, so you will also have to do this. So all the people who speak, you will need to be pretty swift and try when you pass the microphone from one person to the other. Try not to touch the microphone because otherwise it will be very, very loud for people online.
Hong Kong oyster industry is centered.
So Luke, try to make contact with them. So don't do presentation like you say, you talk to them.
Oh, okay. Hong Kong oyster industry is centered deep bay, which is situated on the northwest corner of Hong Kong. It's an industrial area at a junction part. The influx of fresh water, the water is high productive. Besides, deep bay is sheltered and with a.
Is there a chance that you don't read, but you remember the essential points? Because otherwise it's super boring for people, right? If the people are here, you want to either connect to the camera or at least connect to the keyboard. Is it possible that you don't read? Is it possible?
I can't memorize this.
You don't think you can?
Yes.
Okay.
Sorry.
Because it really diminishes the quality of the delivery. If I ask you, without your notes, what is the key point here? What is the key point?
The location of the debate is estuarine condition, and it provides it's
So what you want to say is that in Hong Kong, most of the oysters are in deep bay. Is that what you want to say, right? Then just say that, and then next slide.
Okay.
Don't speak for like too long reading the text. People are going to be bored to death. Like you need to connect and just tell me what you want to tell me. So look at them and just tell them what you want to tell them. Can you please just talk to them? Please talk to them. No, look at them. Look at them. There are people are here. No. This way. Look this direction. People are here. Say the sentence.
The geography of the Hong Kong oyster is located in the northwest corner, and it's the it's an in estuary. It's an estuary area, with which provides the influx of the water, and the water is highly productive. Besides, this area is influenced by the monsoon climate, so it provides heavy rainfall in summer and increase the discharge of the streams entering the bay.
Okay. Next slide.
Yes.
Okay. Do you want somebody to help you with the slides?
I can do it.
Are you sure?
And for the cultivation history of Hong Kong oysters, before 1980s, farmers used traditional culture method, the bottom culture. It's cultivating oysters from scratch, allowing larvae to settle naturally on classes like the wooden post, planted across a tidal flat and leaving them to grow to maximum size. Oysters grow by feeding and planting, but when the water is low, they don't. But when the water is low, they don't have fruits. Then they grow slowly, taking 4 years to harvest. And here are some photos for the different forms of culture, like wood oyster shells, concrete tiles, and concrete posts. And since the method is fully depends on nature, has a long harvest span and labor intensive, so in nowadays farmers use raft culture which learned from Japan. The method consists of surrounding rope or wire from bamboo wrap on the surface, and the rope hang down to the bottom. Young beds sit on strings or buckets, which are suspended vertically from the rafts. And the flattened period is 6 to 12 months. Oysters are allowed free and easy access the natural food, so they can grow fast. And it's easy to build and easy to manage, more effective and less labor intensive. Yeah, that's all.
Okay, so here's the next person. Okay, so you need to be ready. And so when you pass to her, try not to touch the microphone. I really hope that you're all not going to read the other really terrible. So if you can try to speak to people
Or should we
here.
just hold the microphone so that we don't need to take it off?
If you want, you can also just hold it. Yeah, that's also fine.
We will have a problem.
That's also fine. Yeah, just hold it. That's also fine. And if you have a tablet and it's not so, like this, it's not so up here. There's no clicker. That's why I was suggesting maybe you have somebody to click for you if you want to. Just go on the arrow.
Oh yeah, that's. In the natural. In the natural environment, when water gets to become warm in the spring, then the adult oyster begin to spawning. They release eggs and spurs. Once eggs are fertilized, they are freely swimming in the marine water, and they will continue for 24 to 48 hours. After about 2 weeks, the larvae form a black spot and a small foot and move to a hard surface like couch. After attaching to the couch, the larvae are known as spat. Spat take about 1 to 3 months to reach adulthood. After 2 to 3 years, oysters are large enough to harvest. This is the life cycle of oyster.
I don't know if it's better because then there'll be all the cables in front. Because we have audio power. It might be a little bit more messy. I'm just sorry that it's more messy. We could put it maybe like this, so you can see the slide better. But I mean, it's right here as well. I mean.
As an architecture student, we both learn a lot about the oyster cultivation system and contribute our own efforts to it. And even hardware shoppers, we learn marine knowledge and practical construction methods. At the same time, from an architecture perspective, we consider how researchers use these devices and the cultivating system, and then accordingly reorganize their lab space and refine the system.
So in this project, we look into the downwelling system and the upwelling system of the oyster cultivation systems. The downwelling system is mainly for the larvae settlement, for them to attach to oyster shells. And then the upwelling system is for the spats to be raised further to become a larger size. And the conventional system that we are having nowadays are usually having one common tanks, and they are having central channels of water pipes. They're usually immovable and in large scale. They are usually for commercial uses with dozens of silos. And these two systems are always the separate systems. And the prototype that we are making right now is a very small scale combination of both systems, the upwelling and the downwelling, so that it is a movable small scale for experimental system. And we try to combine both systems and make them toggleable with the different pipes, and also installing the sensor monitoring systems.
Do you guys think it's better to show on the TV, or do you think it's better to show the real one? Which one do you think?
No, but it's during our part when we do the physical demonstration.
Because you're talking about this one, right?
Yeah.
So,
But I think if we're showing the real one, it's very hard to.
because we present this one first, and then the big one, right?
We're thinking of just showing the video.
Is it?
And you can like maybe only show 30 seconds.
I mean, if the people are coming here, I think it's nice to switch it on. They see the wire coming on. If it works, might as well.
We do it for my time.
I think that's the idea. People want to see the real thing. Otherwise, they might think that you made some After Effects or something.
I just afraid that it's hard to see.
Is it? We should take the tripod and move closer if you want to. So we need to change the frame, right? Because we can't see it. So just turn like this. We can go to the...
嚇，你講完啦？有冇講到兩個 system 係咩話 ？Spat 同埋嗰個 lava system。
So I would like to share our design process because I think this is the most beautiful part of our project. And then the prototype one, we are trying to design like a commercial use, and then we also design all the pipe work to the to the central. And then we found that there are some failure of our design. For example, how to hold the central channel and then how to hold the pipe, and then the water leakage also is a problem. That's why we do the prototype one amendment. And then when we, I forgot to mention, when we do design, we always do sketch and then 3D modeling and then physical modeling as well. Yeah, for the prototype 2, we also try really hard to make it real for the commercial use, because
First of all, we need to start off with talking about design process. So we start off with introducing a mobile system with a central channel, which is more in between the commercial and commercial. So for the prototype 1 amendments, we separated like the pipe works and then redesigned the silo support and work on the central channel fixing detail. And for the prototype 2, based on the scientist's requirements, we started designing individual controlled set of silos and separate compartments for different experiments. And for the next prototype, in prototype 3, based on the scientist's request of having one experiment for having separate environments, so we started designing as one single module in a 1-to-1 scale. And during the further developments, we started refining the movable rack and the pipeworks, and also design the mesh donuts system, which
the donut system basically is the most important part where to raise oyster, and then actually the concept is come from the IMF heart, and then every details and every size we also consider as well, and then you can see the sketch, so like this.
For the prototype for prototype 5, we started to strengthen the structure of the movable rack, and also worked on the waterproofing of each of the pipe connection. And also we added so in collaboration with the sensor group, they have added the whiteboard back panel and also the center panel. And for the final prototype, for the final prototype, in order to solve the water leakage problem, we work with
So this slide mainly is for design, and then we got, for example, we got the back panel over behind to let people to write something. We got silo, and then we got the movable trolley. So this whiteboard mainly is for the sensor.
And then we're going to show the physical demonstration. They show the physical demonstration. 而家即刻 physical demonstration。即係 open 你個 slide， 跟住我 open 呢個 slide， 然之後 show 呢個。OK。係啊，然之後 show 呢個，然之後。跟住當 show 完啦。點解撈唔到？唔係應該係 open 呢個 slide。係 open 呢個 slide， 然之後我哋再 show physical demonstration。我 control 呢個得啦。但係我哋再高多次咯。
So talking about the upwelling system and showing how it works. So first of all, we make sure the downwelling outflow pipe, which is this valve here, to be off. So then we turn on the upwelling inflow pump and the valve as well. So as soon as the water arrives above the mesh, and then when water reaches the upwelling outflow pipe, it will then recirculate at a constant rate. And then the next one, I'll be talking about the downwelling system. So basically, before we start, we make sure these two valves are off, and then we turn on the downwelling inflow pump. So then when water comes up in the shower, and then we wait till the water level rise above the mesh, and then we can start turn on the downwelling outflow valve. And then we can use the valve to adjust in different degrees to make sure the water recirculating at a constant rate. Yeah, so basically that's it for the manual guide. Yeah.
And we have made an assembling manual that shows the major compartments and also some basic instructions on how to install the system. And the design is the guideline is pretty straightforward and simple, and this is actually like our design intention, which is to make sure that the choice of materials are economical and functional, and also the whole design, the arrangement and the organization of all the different various units are in a way that allows the system to be space saving, to be also light and portable, so that we also have the movable racks at the bottom, and then so that and also it's very essential for design to be smart and user friendly, so there will be no trouble when maintenance is required. And the team hopes that everyone could set up and install this system easily and efficiently.
So I will talk about the maintenance. So there are 5 steps to maintenance. First, to rotate the downwelling inflow pipe and the shower head, and then take out the down nuts, unscrew the bolts and nuts, and to replace the mesh with a new one. And step 3 is to disconnect the downwelling outflow pipe and upwelling inflow pipe, and clean the pipes. Step 4, remove the silo for cleaning. And step 5, remove the pumps for both systems and take out the water tank for cleaning. And just to remind that to double check the water linkage system, with the water linkage problem when after cleaning and when rebuilding the system, and make sure that each part is connected tightly. And if necessary, you can use waterproof tape to tight everything together. Yeah.
And now I'm going to introduce the electric system mechanism and the saucer monitoring of the upwelling and the downwelling system. And first of all, we provide an individual socket for each unit of the system. And as you can see, the socket is fixed at the back of the unit, and the position of the socket can keep itself away from the water. And the socket provides power to the pump and the sensor, and individually to control the switch of the each device here. And maybe and our electric system of the group are made up by the 12 units, and it's easy to find and solve the problems, and each to control individually. And the next, for the structure of the system and the sensor system, we provide a simple strategy to assemble them together. We use the white acrylic and very few bolts to ensure the structure clean and beautiful, and also easy to maintain. And for the next, after a lot of the screening, we finally chose this sensor, which is the multi-parameter water quality monitor. And this sensor can measure pH, ORP, temperature, RHEC, CF, and the TDS. And using this multi-functional sensor can more convenient detect and control the key parameters of our systems. And then before use, we need to test and calibrate our the sensor. And there are 3 right button here. And the left one can switch the mode of the EC, CF, and the TDS. And when you put the probe into the liquid, you can use the left button to select the information that you want to display on the left top screen, a blue screen, and middle button, and can switch the mode of the pH and the ORC. And before use, you need to calibrate the sensor with a series of solutions of specific parameter, and you need to clean the probe. You need to clean the probe here, And after each calibration, and there are two metal holes above the middle button, and you can use the screwdriver here to adjust the parameter on the screen to match the parameter of the liquid being measured. And the right button can the right button can toggle to different units of the temperature. The temperature. And finally, after the after the preparation of the work was completed, and we equipped each unit with a sensor. So there are totally 12 sensors here, and we could simulate different environments of the oyster life and test the factors affecting the growth of the oyster with the precise parameter equipment. And we can divide or group into 4 types here according to the pH, RH, temperature, and the TDC parameter. And you can record the information on the whiteboard here, which can be easy to remove and replace. And then the whole system will be very efficient and scientific under the system.
So here comes the second part of the system. Our system is experimenting on the tube spat growing system. It actually serves as the biology of the oyster from a larva to an adult between the whole cycle. So it's actually a bridging between the outwelling larva and hatchery and also the flopsy system.
So yeah, I need to let somebody else do the.
Yeah.
Keep going. Next one.
Yeah, next slide. So we actually look into some conventional system that we can find in the market. Actually, all of them are quite commercial and industrial and needs quite an amount of space. And yeah, next. And they also need some freshwater supply and filter system to keep the water running. And next slide. So we actually categorize them into a few categories. So one is PVC tubes with hard plastic tube connector, which is quite solid and rigid, but it is all very bulky and hard to handle. And another type is actually a customized funnel where they cast the plastic in the desired shape with a metal. So it creates a perfect fit, but it is very costly to make a mold. But this becomes the limitation of the conventional system and what we want to improve from it. So our system actually have 3 innovations in different scales. So it is a shrink plastic bottle with a quick release system. So in terms of system and operation, it can actually be quickly replaces, and the adapter is universally adaptable. So you can produce and use it almost in anywhere in the whole world. And also the way we use it, we actually use some recycled water bottle, which is a waste of a daily object, and we shrink it to make it water sealed in our system. And the last innovation is about the sensor, where we can have a close monitor of water flow and also different pH value, water temperature to maximize the production of the oysters. So this is a trial one that we have recorded a few days ago. So the whole system consists of 12 spat tubes, each containing different oysters. So the system will take the inlet from the water tank through the pipes, through the flow meter, and to the silos, and after it will drain out of the drainage. So we have the flow meter here to actually monitor how fast the water flow. Um, the unit is a liter per minute, and by this we can actually see how the flow rate have an effect on of our system.
And after that, perhaps we can go through the design and production process of our system. And so in addition to the current commercial systems, we were actually inspired by the image of jelly bean shops in which the tubes are laid out side by side and with a transparent exterior. And we took that idea to develop our design. And prior to our final products, we also developed and investigated a few prototypes where we tried to find out different ways how to lay out the tubes inside the lab. And we also developed some test prototypes at different scales, at firstly a 1 to 10 scale, a 1 to 5 scale, and finally at 1 to 1. For our final design, the main procedures could be divided into installing the frame, the drainage, the water tube systems, and also the spat tubes. And here are some of the materials and equipment that are used for the production, and which are mostly found in local hardware shops here in Hong Kong. And firstly, to install the frame, we made use of the existing shelves in the lab, and where we kind of removed the components, and we also put C-shaped back panels which were made of wood inside and attached them together using L-shaped metal brackets, and also attaching them to the shelf itself. And we also added a paint of waterproof painting. And we also created holders for the spat tubes using pipes which are cut, and also added a bottom rack for the future spat tubes to lay onto. And after that, the second part is to install the drainage system. We created a large drainage tube at the top of the system, and kind of had an open top, and then kept it at both ends, and made holes and supporting brackets to complete it and attach it to the main supporting panels. And after that, we dived into the main area of the water tube systems, and we kind of measured and cut different tubes and connectors, and to create a network of pipes to connect back to the main tank. And the final step is to create and to install the spat tubes. And these images show the different parts that involved in the creation of our spat tube. And firstly, we bought some transparent PVC tubes and also made holes and connectors for the drainage. And we also used the top of the water bottle as the main holder for the mesh, and also the valve connectors. And after finishing these components, they are attached together by heat shrinkage, and then are placed in the system for use. And so these steps all lead to the final design, and this is the final outcome of our system.
So the main variable for our system is the flow rate, which affects the growth rate of the oysters. And so from the picture, you can see that the flow rate from different tubes are varied, and there are two main factors affecting that. The first one is the distance of the spat tubes from the water inlet, and the second one is the amount of oysters added to the tubes. And so in order to solve this problem, we actually paired up a flow meter with the valve so that we can slightly control the amount of water flow into the tubes. And we can actually perform experiments of which flow rate is the most optimum for the growth of the oysters. And because we have 12 tubes in one shelf, we can perform control experiments. So for example, the first 3 tubes are for one flow rate, but with a different amount of oysters, and so on and so forth. And so it becomes a experimental model for the oyster spat production, and to see which one is the best for the commercial.
And then I will talk about the monitoring system of the SPAT system. So the monitoring system consists of three parts. The first component is the sensor that monitors the water quality of the water tank. The key parameters here are the temperatures, pH, and also the salinity. So
when you present the system, you should probably move this one away, right? Can you move this way?
So we know the water quality is still good. The second thing we need to monitor is the flow rate of the water that's coming to the tube. This can be seen on the flow meter here. And the third one is we have two cameras that's monitoring the overall condition of the system, making sure there is no overflow or there is no leakage anywhere. And in the next slide, here's a short video showing how people can keep track of the system when they are away. So these two cameras are connected to a phone app. And when they're not here. I think it's okay for now. And the next page shows how we can use the flow meter. So first of all, we need to reset the readings, and then the two readings here shows the volume that flows through the system and also the flow rate. Flow meter by pressing this reset button. And then we run the system. Here we can read the volume that flows through the meter. And down here is the rate of the flow. When we adjust the switch here, you can see the rate of the flow will change. Become smaller. And we need it to be bigger. And we become larger. Okay, so that's how it works. Okay, that's for the monitoring system.
And for the actual system, we were planning to make 24 tubes, so 2 shelves to study the growth of oysters under different conditions. Dependent variables such as temperature, water salinity, water pH, or food availability can technically be adjusted. For example, the amount of food or water pH can be changed in the master tank. To investigate the growth of the oysters, their sizes and weights can be measured at regular intervals, for example, every week, and record in the form of a table and to draw a graph to see their changes in growth over time. We can then observe how the variables affect the growth of the oysters. And in terms of maintenance, the oysters are living organisms and will produce excretion waste, so it is important to keep the system. Our system is flexible with each tube removable from the system, and the lids can be opened for easier cleaning and for putting the oyster samples into the tubes. And the water in the master tank.
Online in 1 minute. So in 1 minute we will come online. As together we start studying. Sorry to much up. So just so you know, we are running a little bit over time. As of now, we have run already about 40 minutes instead of 30. So basically, all of you need to shorten a little bit. And make sure when you transition that the next person who's going to be speaking, to speak on this side. Otherwise, you have to go under the microphone table. Yeah? So just be ready. Whoever is the next speaker, be ready over there.
Do I continue or?
Yeah, you can continue.
Oh.
Go to the
Oh, okay. The water in the master tank should be changed regularly as they will be contaminated with waste over time. And in commercial systems, there are different ways to clean the water, including biofiltration, which uses nitrification to break down waste products of organism. And the other method is more mechanical, which uses the effects of air pressure for the exchange of water between tanks. But our system is still in testing stage and it's not very perfect, so the water probably has to be changed manually.
So let's move on to talk about the possible future application of our system. So our system uses easily accessible materials and use reusable materials, so which makes our system flexible and adaptable to different environments in any size and shape. And these advantages make our system easy to replicate in other labs. And this is a user manual that we were as a group constructed to walk through all the steps to construct, operate, and maintain the system.
Oh yeah, I don't know if they're gonna come on time, so we're gonna start in 1 minute. Okay.
And to bring our system to another level, we might start to look back to our initial idea of having the system to walk through all the 3 growing processes in order to save the time for moving this oyster around. So maybe thinking of combining the 3 systems on the right.
People are coming right now.
Oh, okay.
Yeah. Yeah. Okay. So this should be the first one. So people are coming in right now. Okay, so everybody has joined. You can call Professor Greg. And there's going to be 2 more structure and 2 more very also coming. So you can, okay, Professor Rajan, you can join. So, okay, so we're going to get started. All right. We're going to see. Yes. I'm gonna hide the controls. Yes. Oh, am I not? Oh, okay. Am I sharing screen? Am I sharing screen now? Yes. Okay. So, so we have everybody in the room. Do you see all the attendees are here? Everybody's here? So you tell me whenever you see that everybody's there, and then we'll kick it off. Yeah, 13 people sounds like. Do you see? Is it recording? It should be. It's recording. Okay, great. Okay, so let's get started. People who are not seeing right now, they will see the recording. Okay, so should I remove the mask or should I keep it?
It's always a difficult call.
Right. Okay.
Better to keep it because many
Yeah, there's a lot of people.
we don't want to be.
Right. Okay, so welcome to the architecture studio called the Floating Marine Laboratory in the collaboration with the SWIMS and also Professor Rajan, who is here. I'm going to give you a quick introduction, so this gives you some context. So I'm very fortunate to have collaborated with Professor Rajan here from School of Biology, who is also going to give maybe say a few words, and I'm from the Department of Architecture. Would you like to say a few words, Professor Rajan?
Hello, hi, All right. Yeah, it's good. Yeah, it's good, guys. I mean, it's my first, I think, second year working with architecture students on the CESAR. It's really nice. Had a great time with you all for the past couple of months. And it's a really fantastic time. I learned a lot from all of you. Be frank with you all. When we started 2-3 months ago, when you gave all these ideas, I never imagined you're going to set up something real stuff. I just thought it's a teaching and course and goes on. So it's very impressive, very exciting, and wish you all the best. I'm looking forward for your presentation in a very different style. And wish you all the best. Thank you very much.
So this is a course about architecture and biology, but we talk about the ocean. And this is very unusual for architecture course. The ocean is where 100% of the life that we know comes from. Also where that captures most of the heat of the sun, controls most of the climate, basically. And also the shipping, as we've seen recently with the canal being plugged. But we're also destroying the ocean in a very, very fast rate. And so this particular architecture studio is looking at the context of Hong Kong specifically, which is where more than half of the population lives in the perimeter of like 5.5 hours flight zone. So what we do in the ocean in Hong Kong can potentially have an influence on what we do in the area. This studio is actually part of a longer term research. I started researching about floating marine laboratory in 2010. And this is what we had built last year. So we basically built this floating lab for 11,000 Hong Kong dollars over 2 days of construction, which is a very low cost for a floating structure in Hong Kong. And all of it is documented online on GitHub. And that was also done by the architecture student master's degree. The reason, the particular subject, that we are focusing on this studio is oysters. Oysters are absolutely fundamental, and especially in this estuary where they have a very important ecosystem function. But they're also disappearing very quickly. These projects that I'm very happy that the student will present to you will continue hopefully next year as we're applying for larger grants and have longer and bigger ambition to move maybe some of those systems that the system will explain to you directly on the sea to even accelerate research and make it even more efficient. What is different from a normal architecture studio, and maybe from biology, is that this one is not architecture for humans, they're architecture for animals. It's not small scale, it's the actual scale. It's not just a model, this is a functional tool that we can use by the scientists. So this is not a fictional thing, this is an opportunity for the student to contribute to research and have an impact. So for all of you who are here, and the people who are online, I would like you to please scan this QR code, and I'm also going to copy and paste this link into the chat. And I'm going to ask you to please fill the Google form. I will share it at the end as well. But I will ask you to look at 1, the potential impact of this technology. 2, is it innovative and creative? 3rd, is it based on hard and well-established research? 4, is it well presented? Does the student communicate to you and you can understand what they say? And 5, lastly, do you feel that it's the result of a good teamwork? The presentation will last for 30 minutes. Then we'll have a quick 10 minutes break because we're actually going to move physically from here to another room, which is much bigger, so we can discuss more comfortable and also more safely because of COVID, of course. And then we'll have a 20-minute Q&A. So you can ask questions to the students. If you cannot stay beyond the 30 minutes, you can leave your questions in the Q&A and then in the chat, and then we'll make sure that the student answer those questions in the recording. And after that, we can have just an open discussion. Maybe we can discuss further collaboration, maybe grant opportunity, or a reference and things that we should learn from this experience and reflecting on this workshop. So that's it. So I will copy paste right now this in the chat, and so I will put it in the WhatsApp in this chat. Sorry, I'll put this in the chat, which is right here. Where is the chat? Chat. Here. Okay, so this is the form. And so that's it for me. And now for the students. be more clear.
Geography of Hong Kong oyster. Hong Kong oyster industry is centered.
Can you just speak louder?
Hong Kong.
Closer, so we can be heard.
Okay. Hong Kong oyster industry is centered around Deep Bay, which is situated on the northwest corner of Hong Kong. It's an estuary area. At the junction part, the influx of fresh water. The water is highly productive. Beside Deep Bay is sheltered and with a large amount of silt brought down from the Pure River and other small rivers draining into the bay. The whole area is very shallow. The depth of water lower than 6 meters, so the oysters are cultivated on this muddy tidal area. Besides, the Deep Bay is influenced by the monsoon climate, warm fresh water condition provided by the heavy rainfall in summer, and the cool saline water in winter is suitable for the cultivation of oyster. And for the before 1980s, the farmers used the traditional culture method, bottom culture. It's cultivating oysters from scratch, allowing the larvae to settle naturally on classes like the wooden post planted across a tidal flat and leaving them to grow to manageable size. Oysters grow by feeding on plankton, but when the water is low, they don't have food, so they grow slowly, taking 4 to 5 years to harvest. And yeah, various forms of scat like oyster shells, concrete tails, and concrete post. Um, since this method is fully depends on nature, has long harvest span and labor intensive, so nowadays farmers using raft culture which learned from Japan. This method consists of surrounding rope or wire from bamboo raft on the surface and the rope hanged down to the bottom. Young species on the string or buckets, which are suspended vertically from the raft. The flattening period is 6 to 12 months. Oysters are allowed to free and easy access to natural food so that they can grow fast. And this culture method is easy to build, easy to manage, and more effective, less labor intensive.
Will introduce about the life cycle of oyster in natural environment. When water begins to warm in spring, adult oyster start spawning. They release eggs and sperms. Once eggs are fertilized, they will freely swimming as larvae, and for 24 to 48 hours. After 48 hours, the larvae grow into a D shape, which is known as the D stage. After about 2 weeks, the larvae form a black spot and a foot and move to a hard surface like a couch. After attaching to the couch, the larvae are known as spat. Spat will take 1 to 3 months to reach adulthood. After 2 to 3 years, oysters are large enough to harvest. And then for the oyster harvesting system, as an architecture student, we both learn a lot from the system and contribute our own efforts to it. From Professor Rajan, sister, and related experts, and even hardware shopkeepers, we learn marine knowledge about oyster and practical construction methods to construct our systems. At the same time, from architectural perspective, we consider how researchers use these devices and cultivating system, and then accordingly reorganize the lab space and refine the system.
So for this project, we look into 2 different systems, the downwelling system and the upwelling system. The downwelling system is used for the free swimming larvae for them to settle. And as for the upwelling system, is after the settlement, they will start to grow in size, and the spat is to be used. The upwelling system is to be used for them to grow further in size before they can move into another system. So for the conventional system nowadays, for the commercial scale, they're always using a common tank, and then they are always having a central water channel. And they're also rather immovable and very large in scale. Like they have dozens of silos in conjunction, and the two systems are separated. So for the prototype that we're working on, we try to be more innovative and combine the two systems together and make it smaller scale and movable so that it can be transported to different areas and for different conditions. And also is more fit for experimental purposes. And also we have individual silos for each of the water tanks so that they have different conditions.
So we would like to go through our design process from our initial prototype to the final outcome. So in all our design process, we start with a sketch and then we refine our design through digital modeling and physical prototype. In our first prototype, initially we were designing a medium scale downwelling and upwelling combined system that is suitable to fit in this lab environment. And we would like to introduce a mobile system with a central channel. And in our prototype 1 amendments, we started working on how we can actually refine our two system and the pipe works from the two system and redesign the silo supports and also the central channel fixing details. Based on the scientist's request in our following prototype, we started designing individual controlled set of separate compartments for different experiments, and following through prototype 2 to the next prototype, in order for them to each silo for each separate experiment, we started designing one single module, one single movable module, and building prototype in 1:1 scale. Furthermore, in our following prototype, we started refining the movable rack and also the pipe works in order to accommodate the two systems within one movable system. And also we designed the mesh donut system for easily exchangeable to exchange the mesh. And in the following further developments, we started to strengthen the structure of our existing movable rack, and also we increased the size of the silo, and also in the collaboration with the sensor team, we have added like the sensor panel and also the whiteboard back panel as well to support the structure and also for day-to-day use of the scientists. In our final prototype, okay, so from what you can see here is our final prototype, which consists of a top silo compartment at the top with a mesh donut in between that is sitting on supports underneath, and then underneath is the movable rack with our water tank, and also there's 4 set of pipes accommodating the two systems. And so now it's more close-up photos of our system, so the overall structure, and then the silo compartments, and also the movable rack with the water tank, and then the outflow pipe of the upwelling system, and then the outflow pipe of the downwelling system and the inflow pipe of upwelling system, and also close-up of the mesh donuts within our silo. And so now we'd like to show you the physical demonstration of our prototype, so you can see through our models. So is the camera taking our physical prototype now? So we will first show you the downwelling system. So the water are evenly distributed through the shower heads into the silo, and then as the water raises up, it will raise up to submerge the mesh where the oyster will be. And once the water level reach over the mesh, we can start. Yeah, we'll show you. So now we have switched on the outflow pipe for the downwelling system, and then so now is the silo. Okay, so now we will demonstrate the other system, the upwelling system.
So basically, there are two switch. There are two switch on the bed to control different pump for each downwelling and upwelling system. So you can see the water now is come from this pump. It's for upwelling system.
Which we will further explain in the next part of operation of the two systems.
So basically, so we're talking about how upwelling system works. So basically, before we start anything, we simply turn off the valve of the downwelling outflow system, which is here, and then we will then turn on the upwelling inflow valves as well as the pump. So just as you can see, as soon as the water rises above the water mesh, and then it will reach this upwelling outflow pipe, and then it will then recirculate as a constant rate. So for the downwelling system, just now the shower hat. So before we start, we make sure these two valves has to be off, so that we would then turn on the downwelling inflow pump. So then as soon as the water rise above the mesh, we will then slowly turn on the downwelling outflow valves. And then we will kind of adjust the valve at the right degree, so that make sure the water can constantly recirculate at the same water level without going over or too below down the mesh. So basically, it's the overall function of the operation.
This assembling manual is actually showing the major compartments of the system, and also some basic setting up instructions. And the manual is pretty simple and straightforward, and which is similar to our design intention, which is to make sure that the choice of materials is economical and also functional. And then it's also very important for the design to be user-friendly, and also people can install and uninstall it efficiently, so that when some maintenance is required, they can like easily pick up. So my classmate is going to talk about the maintenance procedure.
And I will introduce the maintenance of the system, and the video will show how to take apart and clean the system. So there are 5 steps to take apart the system. First, rotate the downwelling inflow pipe, and second, take out the donut, clean or change the mesh, and we could unscrew the bolts and nuts and take out the mesh and change it into a new one. And third, disconnect the downwelling outflow pipe and upwelling inflow pipe, and to take out to clean them. And step 4, remove the silo for cleaning. And step 5, remove the pumps for both systems and take out the water tank for cleaning. And just kindly remember that when rebuilding the system, remember to double check the water linkage issues after taking apart the system and cleaning them. And make sure that each part is connected tightly. And if necessary, we could use waterproof tape to at the joints to avoid the water linkage problem. Yeah.
Okay, when you put and now I'm going to introduce the electric system mechanism and the sensor monitoring systems here. And first of all, we provide an individual socket for each unit of the system. And as you can see, the socket is fixed to the back of the unit, and the position of the socket can keep itself away from the water, and the socket provides power to the pump and the sensor, and individually control the switch of each device. And our electric systems of group are made up by these 12 units, and it's easy to find and solve problems and easy to control individually. For the structure of the whole systems here, we provide a very simple strategy of how to assemble them together. And we use the white acrylic and very few bolts here to get and to ensure the whole structure is very clean and beautiful and also easy to maintain. And for the next, after a lot of screening, we finally chose this one, the multi-parameter water quality monitor, which is the sensor can measure the pH, ORP, temperature, RH, EC, CF, and the TDS. And using this multi-functional sensor can more convenient detect and control the key parameters of the systems. I extract the information from our video and to show the method of the measurement and the calibrations here. And before use, we need to test and calibrate our sensor. And there are three red buttons on the sensor, and the left one can switch the mode of the EC, CF, and the TDS at here. And when you put the probe into the liquid, and you can use the left button to switch the information which showed on the blue screen to switch the mode of these parameters. And the middle buttons here is the pH and the ORC button. And before use, you need to calibrate the sensor with a series solutions here. The versified parameters here, and you need to clean the probe after you calibrate some specific parameters liquid. And there are also two metal holes here. You can see in here the metal holes here above the middle button, and you can use the screwdriver to adjust the parameter on the screen and to match the parameter of the liquid being measured. And the last button is on the right, can toggle to different unit of the temperature. And the last one I show after the preparation work was completed, we equipped each unit with the sensor, and so there are 12 sensors here, and could simulate different environment of the oyster life, and with a precise parameter experiment. And we can divide our system into 4 types according to the pH, RH, temperature, and the TDCs here. And each type can simulate the environment with 3 different parameters. So you can record the information on the whiteboard and write some key information here, which will be easy to clean, remove, or replace. And the whole system will be very efficient and scientific under these systems.
So here comes to another system, which is the tube spat growing system. It is a system that actually helps to grow the oyster from a larva, which is around 14 days old, to adulthood. So this process is around 1 to 3 months. Yes, it is actually between the upwelling larvae, which is that system, and to the flopsine nursery hatchery, which is usually on the sea. So before we design our system, we actually look into some very conventional oyster hatchery practice. So these images are some that we found on the internet about how they actually grow the larva to a spat commercially and industrially in quite a large place with fresh water supply and also close monitor of the condition of the oyster growing condition. And we actually categorize them into two separable types. So one is with a PVC tube with a much solid connection of the system, but it is quite bulky and also very costly to make. Another one is actually a customizer funnel where they actually cast plastic with a metal mold to make it perfectly fit. But however, this is, although it is quite fit and very ideal in terms of using it as a system, but it is very hard and also quite expensive to manufacture. So what we do is actually we add some innovation to the system in 3 scales. So in terms of operational innovation, we actually use a very light and elegant quick connection, a connector to merge the system to the tube. So it can be very universally adaptable. You can build it in anywhere in the places and it can still work. And the choice of material we make it actually, we change the connection part in with a plastic bottle. So this is we reuse the daily objects. So we can actually be very easy. And also we actually use the plastic shrinkage method to make it perfectly sealed with a very low cost way of fabricating it. And the last is the sensors. So these sensors can help us to remotely monitor the condition of the system, and they can grow very easily. And this is a demonstration of how the system actually works. So you can see the water is being taken in from the main tank below through the pipes, through the flow meter, and then to the spat tube. The overflow water will actually reach the drainage pipe and will go back to the main tank as a circulation. And with these flow meter, we can actually see how the difference of each system works, and to see also test on how the variable as water flow can have an effect on the growing system.
And so after the demonstration, perhaps you can quickly go through our design and the production process of the system. And apart from the commercial systems available currently, we also took inspiration from the image of a jelly bean shop in which the transparent tubes are laid side to side. And we took that as the idea for our design. And we also made some prototypes to think about how to lay out these pipes inside the lab. And we also worked in different scales, for example, first 1 to 10, 1 to 5, and then at a 1 to 1 scale. And the main procedures of constructing the system can be divided into 4 parts. Firstly, the main frame. Secondly, the drainage, the water tube systems, and finally the spat tubes. And here are some of the materials that are used for the construction and also some of the equipment. And the majority of these can be found in local hardware shops in Hong Kong. Firstly, to install the frame, we made use of the existing racks that are available in the laboratory and amended them. And we also bought wood panels and created a C-shaped back panel in order to hold up the structure of the whole system. And this is us attaching the metal, the wood panels together, as well as applying waterproof paint so that the wood doesn't wear out. And we also created a spat holders in order for the panel to hold the spat tubes. And these are created with cut open pipes in which they are then drilled into the back panels. And at the bottom, there's also a rack in which we use, at the bottom, there's a wooden rack in which we use to hold the different spat tubes. And after that, we installed the drainage, which is at the top of this system. And we cut open a large drainage tube and drilled holes and capped the ends at the both sides. And also added brackets in order to install that into the back panel and hold up the drainage. And the tubes that you saw just now are also part of the water tube systems. And for that, we firstly created the network of tubes at the bottom, which are made from different hoses, pipes, and connectors. And after that, the main part would be the spat tubes, which I think you've just inspected earlier. And these are some images that show how the different components that are in these tubes. And firstly, they are created by buying PVC tubes of a certain diameter and adding the drainage system top, as well as the other part using the top part of a plastic bottle. And for the plastic bottle, we added a mesh and also different valve connectors. And these, the two parts, the PVC tube and the plastic bottle are then melded together using a heat shrinkage system. And that is how the whole spat tube is completed and inserted into the design. And so these are the steps that lead to our final design.
So the main variable in our system is the flow rate, and which affects the growth rate of the oysters. And as you can see from the demonstration just now, and also the image here, the flow rate varies across different tubes, and it is mainly due to two reasons. The first is the distance of the tubes from the water inlet, and the second one is the amount of oysters added to the tube. And to solve this problem, we actually pair a flow meter with the valve, so we can actually slightly adjust the water flow entering the tubes. And we can use this as experiments to see which flow rate is the most optimum for a certain species of oysters, and also perhaps a different size of oysters. Yeah.
And then I would talk about the monitoring system of the whole thing. So the monitoring system consists of three parts. First, sensor set that monitors the water quality of the water tank to ensure well-being of the oysters inside. And the key parameters this one monitors are water temperature, the pH of the water, and also the salinity. The second thing we need to monitor is the flow rate, as you can see with these things. I'll talk about them in more detail in a second. And the third thing is we need an overall image of the whole thing, even when the researcher is not in the lab. So we installed two cameras. One is here to see the readings, and another one is here to see the overall picture to make sure there is no leakage or overflow anywhere. So this is a demonstration of how people can keep track of the whole thing via two cameras on their phones using an application.
Hi everyone, this is our camera system for the spread.
You can see there are two cameras here.
First, we can have a view of the spread system, and we can go to the full screen to have a better look of it. And then we can also adjust the camera through the app. And let's go to the sensor. And we can also press the microphone to talk to the people in the lab.
Okay, that's pretty much it. You can. You can see what's going on even if you're not there. And here's a quick demo of how to use the flow meter. First, we reset the flow meter by pressing this reset button. Run the system. Up here, we can read the volume that flows through the meter. And down here is the rate of the flow. When we adjust the switch here, you can see the rate of the flow would change. It would become smaller. And if we need it to be bigger, then we just make this one larger. Basically, that's how it works. First, we can reset the flow meter.
Actual system, we're planning to do 24 tubes, so two of the shelves to study the growth of oysters under different conditions. So in our case, it's mainly the flow rate. But technically, some of the independent variables can also be changed. For example, temperature and water pH, which can be adjusted in the master tank. And to investigate the growth of the oysters, their sizes and weights can be measured at regular intervals, for example, every week, and record the data in the form of a table or a graph to study how these factors affect their growth. And since oysters are living organisms, they will produce excretion waste, so it's important to keep the system clean. And our system is flexible with the tubes removable from the system, and also the lids are openable for cleaning and to put the oyster samples inside. And for the water, it still requires us to manually change the water regularly to keep the water clean. And in commercial systems, there are several ways to clean the water. For example, biofiltration, which uses the process of nitrification to break down excretion products from the organisms, and also a more mechanical process using the effect of air pressure for the exchange of water in the tanks. But for our system at this stage, it still requires us to manually change the water.
Thank you. So let's move on to talk about the possible future application of our system. So our system uses material that are very easily accessible and also reusable. So it's very flexible and adaptable to different environments in different shapes and sizes. And so it's applicable and easily replicable in other labs. And oops. Okay, so this is the design manual that we as a group constructed for people to easily follow the steps to operate, construct, and also maintain. And to bring our system to another level, we can start thinking about how our system could be bring on site, and also how it can be incorporated in existing systems, like as stated on the right. And also this is an initial sketch that we start to think about, like how our system can incorporate both upwelling and downwelling, and how it can start to go through all the growing processes of the oyster from like when it was a baby. And so I think the bigger question of our project is whether it's possible to bring our system to a bigger picture in a commercial scale and to contribute to the environment and at the same time to the industry itself. So we believe that as long as we combat these challenges, both of our system could become a prototype for the industry in the future. Yeah, thank you.
Caesar, we can't hear you.
Your turn.
So I think it's really impressive what you've achieved in such a short time, and I think the merging of biology with architecture is really quite a challenge. And I'm sure that you realize some of the challenges of trying to use organisms and thinking about how to keep them alive. I really like the way as well you've been looking at reusable objects, simple objects which can be changed over and which can be applied in a very general sense. And I think that is very sustainable in the long term. I think the most exciting thing, though, is trying to think about the future, what actually your applications can go forward, as you've just mentioned at the end. And I think it's something which Rajan and Kamani and the other people in SWIMS are very keen to try and see this relationship. Getting your expertise and your input to try and help us solve some of our problems is really important. And I'd like to thank Cesar as well for having the vision to bring these things together. So I think you've done a fantastic job. And I've certainly stolen a few of the ideas when I was watching earlier to try and show my students as well, so we can actually apply some of these ideas of work which we do. So thank you very much for that.
We can hear you, Caesar. Yeah.
What I was saying, so Kamnani is a PhD researcher here. And what I was saying is that she is a person who would be like a typical user of the system. So what I was hoping is that when the student demonstrates that they take the tube out and it just clicks out, I was hoping you'd be like, yes, inside of you. But I don't know, how do you feel about this system? And what do you think it can be improved? Because you'll be a user for that system.
It's very impressive because I was giving them instructions in the beginning, like what we want, what, or like how what we expect, like easy to clean, easy to maintain. And then I really like how you have incorporated all this like sensors, because whenever we do our experiments, we like manually check the pH, like whenever we need, like maybe once or twice a day. And then we always grew in tanks like this, small like tanks here, you know, like this is how we grow oysters, like larvae in big tanks and oysters like this. So this is it's been like a dream for our lab to build a system like this, to build a hatchery like this for several years. Since I came here, like we were thinking about this project, and finally I'm so happy that you guys made our dream come true, because it's like we never work with such fancy systems. We just always use like some boxes, and we have to build all these on our own. Every time we do our experiments, we have to connect pipes, and we spend quite a lot of time doing that, building the system. So now we have this, it reduces a lot of our time trying to build like the system every time we do, like, and then whenever we do it leak, and then suddenly one day it'll pop up and we are away. So I really like the idea of like keeping a camera, because sometimes we'll go away and then the next day come back, or weekends when we can't come, we'll be really worried. Oh, is it still like working, running? Now if you like you have the camera, I really like it. We can monitor and be at peace, like, oh, okay, it's working. So I really like the idea, and I look forward to use it. And then maybe if I have like, as I use, if there's any improvement required, I can contact you guys for help. Or as you said, it's also easy, like you gave a manual, so I think it'll be really useful. Really good job. Thank you so much.
So for the people who are online, we'll take a picture and then we'll take a 10-minute break. So if you want to start to take the break, you can take the break right now. Yeah. Need somebody to, who can take the picture though? Yeah. I think we're gonna have to get double layers. Yeah, maybe. I'll never be able to get that. Yeah, I'll sit down because with the system to see. Yeah, that's right. Yeah, no, I should have so you can see the system. Yeah, the system. Like that. Oyster. You see that one? And you can change to zoom one. Yes. Well done, guys. Well done. Thank you so much. Thank you. Everybody. So, thanks a lot. Can we take a 10-minute break? I mean, actually for us, we have to basically pack up and go because we only have 10 minutes. So basically we pack and then we meet on the other side. If you have time for like a 7 minutes discussion, maybe you can give us some more suggestions. Maybe very nice. It's going to be harsher on us. That would be super helpful. Of course, people online, stick around. We'd love to have your questions. And then I'll have a discussion with you. So we see you in 10 minutes. We're going to change rooms. So for the people online, we're going to change room. And we see you in 10 minutes. If you don't have the time to stick around, you can leave your question and then we'll ask them to all the students. Okay, see you in a few minutes. So time to pack up. so much for joining the class. Right. So we are back in session. So thank you so much for all of you who have been waiting. Thanks a lot. We have, I think, a couple of questions. Or do we have any questions? Oh, no, nothing in the chat. Oh my gosh. All right. There's a colleague of mine. His name is Christophe Krola, and he always has really, really good question. And there's another colleague, Moussine, also has good question. I'm sure you can kick things off.
I'm happy to ask a question first. I mean, very interesting presentation. I'm very happy to see that the students are being exposed to the nitty-gritty of what it really takes to go into this type of work, because very often we'll see projects or even thesis projects that work with a narrative-based approach where students speculate about what it takes to, say, for example, do an oyster farm. But to have an opportunity to go really into the depth of its requirements is a great learning opportunity to see that there's more to it than often meets the eye at first sight, but to also see that you actually have access to it and that you can actually positively impact by you know, taking the bull by its horns and actually trying to see how you can come up with solutions that otherwise they might not even be aware of. So I thought that was very, very interesting to see. It's difficult for me to give feedback in a way that I would normally do in an architectural project, because it's so much almost a mechanical engineering or an engineering approach to a biological problem with electronic components, typical engineering components. So it's a bit difficult for me to really dive into where the criteria are for success, where the criteria are for improvement or evaluation. But I want to kick off with maybe a bigger question. There's this very interesting author that you may have heard of, Yuval Noah Harari, who wrote a seminal book called *Sapiens*, and he wrote a few other books. In one of his recent books, where he gave some pointers for the 21st century, he makes this comment about the Anthropocene, where we all live in, and how the whole planet basically lives is basically used now in often in function of humanity, or that there's not even a conventional concept of what nature or natural is anymore. And in that book, he talks about the most successful biological species that you'll find on the planet. Of course, we're doing quite well. But for example, also cows and chickens and pork and pigs are doing really well, because they just have a huge amount of them in the planet. It's just that their lives are utterly miserable because they're being farmed for their meat, they're being slaughtered. But if you would purely look at the quantifiable numbers of it, they're actually quite successful as an evolutionary species, because they have been able to procreate to the scale that they have. And then I found a very, very interesting comment when you start to think about architecture not for humans, but for animals or for nature. It raises a question about what the criteria are that you were to design with. And especially with oyster farming, again, yes, there's also the farming component of it. We'll eat the oysters, we'll use them, we'll have the pearls that come from it. Yes, they clean the water. Yes, there's a great benefit of it. So it's not really a criticism of that, but it's more of a questioning of the framing of the studio. When you say architecture for a particular species, how do you identify, other than the purely quantifiable, what a qualitative drive could be for a species? Because when we design for humans, there's a difference with, for example, mass housing, where the main goal is just to give everybody a roof over their head and give them plumbing and electricity, so that, you know, the worst living conditions are met, are no longer a problem. And then designing what people could call architecture with a bigger A, where you're also starting to go into the qualitative components of living. So living is not just becoming an engineering problem that needs to be solved. It becomes a broader qualitative problem that needs to be solved. And of course, oysters, very different species. I want to maybe open up the discussion and get some feedback from the students, how you feel about this idea of architecture for non-humans, and whether or not there's also a difference there between an engineering approach and maybe a different type of approach, because all the project that we saw until this point, they were very problem solution driven, which is fine. That's a start of it. But there's still a bigger question at hand potentially. If you want to take this project further, if you want to scale it up, if you want to implement it, how would you improve it? How would you increase its impact? And maybe by shifting outside of the qualitative parameters and maybe into some of the quantitative ones, on which level your project might impact, there's some food for thought there. So it's not really a question. Maybe Caesar's more a question for you actually then.
Reflect that question to Kamnani, because you work with oysters. So for example, we didn't really look at how well do they feel. We didn't look at the well-being of the oysters. But are there things that are beyond the basic sensor that we measure, about the lighting, you know, the certain things that we don't really pay attention that actually improve their quality of life, quote unquote?
So the system that you guys have built is one we will be using for our experiments. So we will be using for our experiments for studying effects of climate change, parameters like pH, proxy for like ocean acidification and ocean warming, temperature, salinity, different salinity conditions and stuff. So that's why we need to measure those parameters like accurately, and all the other conditions. For example, different species require different salinity, and so these are the three main parameters that is required. Other than this, we also measure like the total alkalinity of the water. That we collect samples and then we do titration when we measure. So it's not easy to just like measure automatically using sensors. So whatever parameters that are possible to like measure directly from using sensors available. So that are the parameters we asked you to put sensors. And another thing is, other than experiment, whatever you guys have built will be used for producing oysters spats for Hong Kong oyster farmers, because mainly now Hong Kong oyster farmers get their seeds from mainland and then they do. So there's no oyster hatchery in Hong Kong. So one of our goal is to build the oyster hatchery for Hong Kong. So in the future, the farmers need not rely on mainland for the supply of seed. And other than that, on the conservation aspect, there's also in our university, in our department, there's oyster restoration projects going on. So for that also we can introduce seeds using this experiment. And the difference between culturing oysters in the field and in the hatchery is under this climate change era, the main challenge is the early life stages of oyster, such as the larval stages, are very sensitive to changes like climate change, like ocean acidification, different parameters. So it's really important if we need to conserve the species. Like that's why the hatchery plays a really important role in protecting the early life stages, and then we put them in the field. Then they have better chance of survival. And of course, the conditions will be different between the field and the laboratory. And it's really difficult to maintain oysters after a certain size. Maybe we can maintain them for 2 months maximum after they hatch. And after that, it's really difficult to maintain them in this system, no matter like how perfect the system is, because they need really lot of food and they generate a lot of waste. So it's really difficult to maintain with all the requirements. So whatever we are doing now, it will be for early life stages, which is manageable, and it will be more stressful for them in the field because of varying conditions. So we provide them the optimum conditions in the lab, and then we save them, give it to the field. So you guys did a good job in contributing to this.
I'd love to hear from the students. Like the student we have is very kind of engineering. But has somebody well within this system, but the thinking about this more architectural aspect of the quality of life, also of the stages, then you have this thought to a lot of people share. Everybody thought about this also. I mean, for example, I know that you're all about ecosystem and you're all about like diversity. For me, for one of the things that shocked me is that when you study species, you study them in isolation. But in nature, they're always surrounded by other species. Have a danza, they have a symbiotic relationship, but there are other species. And so, and I assume that a lot of those other species have contribute to them becoming better, or it's just that if you study human nature only on prisoners, it's about the metaphor, but you get the idea. If you decide that we understand the nature of human being by just studying the prisoners, it doesn't really give a good picture. Like, is there other methods to study more complex system or multiple species within the same environment?
Yes, there are. If your goal is to study the complexity of the problems, but it's really difficult to design an experiments incorporating all the different elements. For example, oysters require, for them to settle after the larval stage, they need like biofilms, like they need the cue to like decide where to settle. So if you have a plate with biofilm and then a plate without biofilm, they choose the plate with biofilm. They think it's good for them. So, so there are parameters like that. There are also studies that look at light and the color of the tanks that they grow. So for example, we mainly do like use dark tanks for them for the larval stage, and there is a difference. Like they prefer like certain colors and certain structures. For example, if you have like a smooth surface versus for them to settle down versus like a surface which is rough, they prefer the rough surface. It's very good. So, but for our goal, as I said, we try our best to incorporate all those different elements. But also we have this commercial element to it as well, to like for the livelihood of the farmers here. So it's just like whatever we can do best, because to include all the others for our studies, our lab, we mainly do molecular level studies, which will help in like understanding their the evolutionary behavior, like all the other different things. So it's really difficult to design an experiment incorporating. It becomes more complex.
You have also questions for them, because we hope also it can be in collaboration. Of course, we want the architect can learn a lot from the biologists. But are there things that the biologists wonder from the world more like non-architectural, when you see the work that you question you have for that? I don't want to put you on the spot, but if you have something that you
I have some suggestions for the system which I can tell. So I really like it's like removable, like it's detachable and cleanable. But then so these are like very specific questions about like now you have the what is that like? No, the inside. Instead of oysters, you have beads. Yeah, beads. So with just that, it's fine. It's flowing fine. But then with oysters, they generate waste, and we feed them. So that will like in the other system, the small system of filling, downwelling, that one, it's fine. You can remove the filters. But in this system, I was just curious if it's possible to like change the filter, because it seems like it's really at the bottom, and I wonder if you need to like just clean it, and even if after cleaning, if it's clogged,
and you cannot use that, then is there a way to change it, or you have to change the whole tube? Or and also another thing is the outlet, the drain is open, the water, the drain at the back of the system is open, right? So it'll maybe it'll get dirty, something might fall in, like, yeah, dust or something. So I was wondering why you left that open. Is there any design like requirements? Like I expected that. So why?
I'll answer the first question first. You mentioned about whether the filters are changeable. I think that is also possible. It's just the way we try to take on the manufacture or the fabrication of the system is to try to use some more adaptable use of data objects of such connectors to have more easier access on how to build a system. So we actually start from the point of fabrication. We haven't actually tried to run the system for months or 3 months. Yeah, but I think that can also done in the later amendment if we cannot remove it. We can actually only take out the plastic bottle and then change it. It doesn't really take that long. Yeah. And for the second, is it about the water drainage? The reason why we leave it open is because we are not sure about the rates of the flow, water flow. We don't know, we don't have a sense of actually how much water do they need for a certain period of time. So the reason why we leave it open is that we can change it anytime, like the volume of the drainage. Yeah, because in the first trial, actually the water, because the hole of drainage is not fast enough, not large enough, so the flow that they are being drained is not, they can't be drained away quickly, so that the overflowing happens in the top, and then we decide to change or iterate with the whole of the drainage and also the diameter of the pipe, and then to have a test of how it goes. I think it is because we don't really have time to actually test or experiment to actually grow the oyster for months. So we don't have that. So we kind of leave it as a. We kind of want to leave it open in this stage before we actually step into the experiment part. Right.
We have other questions from the people online. I can see there's Philippe, Greg, Anika, Grace, Michela from Indonesia, who is coming from Indonesia. Do you guys have some questions you'd like to ask? You can unmute yourself, or you can type the question, whichever you're more comfortable doing. Oops.
Okay. Hi, it's Michelle. So I don't really have. Hi, how are you, Caesar? Good to see you. Like it's really exciting. I just want to. I guess it's more about input more than questions. Like maybe, if you already figure out the technology and later on, Oyster is going to be like, a drive key products, and you realize that, this actually has different functions, right? So maybe you can think about later when applying it and the output, don't stick to only one. Like example, maybe for the ocean coast or ocean water that is dirty, that you want to clean it, maybe like, you know, customize it so that the purpose of that oyster when you actually apply it in that area is going, the purpose is to clean. And another one, if you're gonna think about the hatchery, and maybe think also about things like logistic-wise, clean water, because, you know, if you're talking, because I know for a fact that in here in Indonesia, I have friends who do hatchery for goropa, snappers. And so it's two key components that I see. One is, of course, the source of clean water and space. And second is, you know, the location when they implement it is actually in between a strait. So it's protected from like factors like currents that can destroy it. And also it has a clean, it has a good water currents. So it's a natural like cleaning mechanism, because when you have a flowing water, then automatically the microorganism and the cleaning factors is gonna be turned on immediately. I think that's it for me, and good luck, all the best.
Yes, so Michela, and it needs to be said, so she actually has her family are actually fish manufacturer. They have many ships, and they actually they basically have a whole industry of fishing. So she's actually very knowledgeable about the stuff from an industry perspective. Thank you so much, Michela.
Of course.
Philippe, I'm sorry, I muted you. I accidentally muted you.
Hello, everybody. Thank you, Cesar, for the invitations. I have some questions, but it's more in the general point of view. I'm an architect as a background, and now I'm working on environment, and specifically on the complexity side of the environment. So I was wondering, just as a methodology, I'm very impressed by the kind of results you have as a group. Group thinking is very powerful. But it's just a way, questions how you organize to solve problems. Nowadays, we tend to solve technical problems because we have very rational approach of the world. So we identify one problem and try to solve one problem. And very often, actually, even when we solve it very well, we end up with a lot more problems than side problems. That's what the reductionism approach of our society is doing. For example, the beef that Christoph was talking about, the chicken and the beef, we solve the problem of producing it a lot. Same for wheat, but we end up with a massive problem globally. So when we take oyster as a product itself, which we tend to scale up, as we say later, I think it's very important to, you stated at the beginning of your presentation that it's very important for the environment, for global, I mean, the function of the oyster in the environment, and et cetera, et cetera. So that's a good, very good premise. But then you solve problems after at the very specific level, like water quality, you know, pumping, et cetera, et cetera. And so it's very easy to get lost on very small details and solve them very well. The problem is how do you come back to the original question, which is a large environmental ones. In your process, do you have some ways to integrate, to go back? There's different level of approach of the things, a very strategical one at the environmental side, then a more precise one, a tactical one, and then a technical one. And you tend, I think, to work very hard on technical side and solve it very, very well. But I wonder how often do you go back to the tactical and strategical one? How do you integrate that on your thinking regularly to re-input to see that, you know, where you're going globally? Because I've seen that on the field very often. I'm working with people, scientists, etc. And then even scientists tend to solve problems very specifically, but it does applied on the field, which I'm doing. I'm doing applied science on the field. It doesn't work. So all the energy you're spending is really commendable. I mean, I'm very impressed by the capacity you have in the university as a thinking group. I think it's very important to try to get focused on the larger scale and at the same time applicability on reality. So I was just wondering, as a group, how do you integrate that in your process of thinking, elaboration, research, and solution finding? Thank you. It's a question for Cesar as well as your students. Huh?
So first, I will take the blame because I don't think I introduce the students so much to that sort of level of thinking. So I will take the blame because I think it was my job to give you a bigger picture. But because the bigger picture, the course was more ambitious actually, was to actually go outside and build something floating on the water. And we sort of reframed it because we realized we didn't have enough time. But I did ask the students if they have a better grip of this technology, is how they would want to see it being applied or maybe scaled up. So now that you have worked like very much on the technical, scientific, I would love to maybe have your vision of how you think this could be implemented, or what you imagine you could do with it. It's just like as an architect, today in this course, you learn how to build a brick. And now I would asking you, okay, how would you build a house with it? Like how now you have this component, what would you be excited to build with those oysters and those systems?
The interesting part is to actually move it to the sea. Like it's a different kind of condition comparing to the lab, where you have to solve different system of drainage, water, electricity supply, which is actually very well provided on land or in the lab, but it is very hard to notice that there's so much work, like the underground piping works that are very hidden from us. So I think that the challenge point is to actually move to the sea to see how the different levels or different areas of land or resources we can occupy. Like it is very different to cultivate or hatch the oyster in a very shallow level or maybe on a beach. And also it's very different to do it in a very deep ocean, of how you actually stabilize the whole structure or actually bring the resources or bring the facilities from the land to the sea. Yeah, so I think it is about how we go from land to sea to different scales, and also how to bring the resources, bring the facilities together.
So we have a question. I think sort of bridges some of what Philippe is asking, which is a question from Grace, who works for Oyster SOS. So it's a nonprofit, I think, that does a lot of restoration project. Grace, if you want to ask directly the question, or I can ask it on your behalf.
Yeah, I'm so sorry, but thanks, Cesar, for inviting me to this talk. It's really rewarding to know that resources with such basic the types of materials that you guys selected and the final product that you managed to produce it's really impressive, and it's quite accessible. And I think if we can have a chance to see the manual and improve it, I think it would be a great model for lab users and different other parties as well. But as like a restoration project or just some ideas, I would just like to know if it's possible to perhaps include some different extra features targeting the specific user. Say as a restoration project, we might want an extra feature to put shells where the spats can have space to settle onto the shells, and we can directly take the shells which already have spats on it and just put it out into for deployment. So I was just wondering whether it's how feasible is that, how much resources are those gonna take, additional to the features that you already have. But overall, really appreciate your effort. Thank you so much. And it's a very nice session and I learned a lot. Thank you.
Because this is the specification that we gave. So the idea of our lab giving this instruction is because we mainly do experiments, and also this is for Hong Kong oyster farmers. We produce seeds for Hong Kong oyster farmers, and the parameter that Ms. Grace is interested in will be ideal for conservation work, because for conservation, when you deploy oysters, you want them to be settled on like a cluster on shells. But the specification that we gave you is for single oyster spat production, because single oyster spat has more commercial value. So for commercial purpose, this system is good to make single oyster spat and grow them. But for restoration or conservation work, there's no need for single oyster. So for that work, it'll just be enough to have like a huge tank with the racks like on top, where you can hang the shells, and then where the oyster larvae can settle, and then you can just take those and then deploy in the field. So I think it's important for you to know, like, this system is, the specification that we gave you is mainly for commercial and research purpose, and for the conservation purpose. But this might not be suitable, so you need to change according to the requirement. So.
I think we have a similar question that comes from Annika. Annika, do you want to ask your question?
Hi, yes, thanks everyone for the great presentation. It's very amazing to hear your new design. Because TNC is working closely with our local oyster farmers as well to have some sustainable aquaculture projects. So we kind of learn about their challenges in the past. And I'm just curious if the design or even the whole hatchery project is designed to be carried out by the local oyster farmers in the long run. The reason that I ask is there is need of training to our oyster farmers in order to implement it. But if we design it to be like having some lab condition or some new comers to operate the hatchery, then it wouldn't be a big problem. But if we want to target on the oyster farmers to operate themselves, then there's need of a more or much easier way to operate the whole system. Just a simple question. Who is the audience, the target audience of the user of this system?
Maybe I try to answer. I think when we are making the system, we are aiming for like allowing the oyster farmers or like people not from the with a high educational background to be able to build and use the system. So we have a manual to show that how the system could be built up like step by step, even and using the materials that can be found in hardware shops that are easily accessible. Mm-hmm. And so the main goal is to let them to have a very like a startup by themselves. So it doesn't require like high-tech support to do that. And I think like right now the system is in the lab, but then if the whole system is replicated somewhere else, it still be able to work. And those sensors are like quite easy to be used and to be monitored. So like most of the conditions can be controlled as well. Yeah.
This
Yep.
Maybe I'll ask the question a little bit differently. I think it's the same similar question as Annika, but now that you're familiar with trying to do the experiment with a very precise measurement to maximize the yield, right? How many oyster can you make? But if you are designing now that same system, but for oyster farmer, the villager, how different will it be? So maybe as an architect or designer, that's maybe more the question how would frame it. Like how different will it be? Like would it have different, you know, like maybe you could have other voices. How different will it be? What would be different?
So I think I mentioned, like I touched on a little bit on this part when I was presenting just now on the future application. So I think in the initial stage, we also thought about how we can actually like maximize the potential of our prototype, like not just doing the like upwelling that we are doing, but instead we want to incorporate all the stages of the growth of the oyster, like most of the stages of the growth of our oyster in our system. So for example, maybe we have a string attached at the top of the cap, and then we will have it attached to the string. So the whole thing can be taken to the oyster farm and they will grow on the string. So it will be easier to operate, and also it will be more mobile to be moved by the oyster farmers. Instead, it won't be so troublesome to move on to one system and then we change to another system when it's another stage of growth. So yeah.
Yep, thank you.
I think all the questions from our guests have been answered. So Philippe they said that for now the target community may be the scientists. So maybe that answered that brief. Yes, maybe Philippe, you want to ask your question yourself, and then we should let them go. I think this should be the last question because we're already past the time. Philippe, do you want to ask the question?
Yeah, so I thought the last questions were very pertinent about the community target. And I think maybe you should start from there, because a lot of solutions are found in laboratory that don't work. Yeah, I think it's very important maybe next time to start with the community, because everything we try to solve is society, I mean, human beings based. It's not really anything else. So we have to work from the human perspective, not the theoretical ones. Well, that's my last question. So, well, it's a suggestion. I don't know.
Thanks so
Thank you
much.
very much. But
Totally
community
agree.
target, I think it's very important as a starting point.
Yes. Yeah, maybe that's something that we would love to learn as well from you, is like how do you interact with the oyster farmers? Because you work with them, and like, do you actually give them the oyster larvae, or do they ask you a specific type of larvae, for example, with specific characteristics? These are things that we would love to get more into, maybe in a future collaboration. I want to close as well because I know the students are hungry. They want to go have lunch. Thank you so much for the time. So I had a discussion in the walking in the corridor with Kamnani. And so you are about to present your PhD, but you also may be interested in doing a postdoc, and many other students who were a collaborator who gave you some feedback and insight. Actually, they are going to be using this instrument. And so I don't want to put you on the spot now. I put pressure on you to continue, but this is definitely an ongoing conversation. And so if you're interested in continuing to research at the intersection of architecture and marine biology, this project is just a start. And I'm definitely going to keep working on this. So there will be infrastructure and funding and opportunities to continue on this project. So yeah, thank you so much, Kamnani, for spending the time with us. I know you're super, super busy. Thank you so much for our guests coming from all around the world. NGO and scientists and entrepreneurs, and we really, really appreciate your time as well, and your question. They really help us to move forward. Thank you so much, everybody. Thank you.
Thank you, Cesar.
Bye.